In this problem, we're asked to compute the area bounded between e to the x and e to the negative x on the interval 0 to 1. So e to the x is the yellow function here that's on top in the region of interest, and e to the negative x is the red function, and that's the lower bound of the region of interest. And we start by visualizing a little area element that I'll call dA. And dA is just a thin vertical slice, and that's well approximated by a rectangle as long as it's a thin enough slice. Now we just have to write down the area of this little rectangle, and I need the height for that. And this is where the order of our two functions is important. I have to get the height by subtracting e to the x minus e to the negative x. So because e to the x is on top, that's guaranteed to be a positive height contribution. Then the width of our little rectangle, we just call that dx. It's a little differential contribution in the x direction. So the area of a rectangle is simple, and we can write down that dA is just given by the height times the width, e to the x minus e to the negative x times dx. And then to find the total area, well, integration is really just a summation device. I sum all the area contributions, all the dAs. And because dA has already been expressed in terms of a single variable, I can go ahead and put in my limits of integration. X is going to go from 0 to 1. And dA is e to the x minus e to the negative x dx. And we're ready to just guess the antiderivative and wrap this thing up. So the antiderivative of e to the x is just e to the x. Antiderivative of e to the negative x is negative e to the negative x. That's going to kill that minus sign in front of it. And then I evaluate that sum across the limits of integration. Plugging in the upper limit, I get e to the 1, which is e, plus e to the negative 1, which I'll probably rewrite as 1 over e, minus, plug in the 0 for x, and I get e to the 0, which is 1, plus another e to the 0, so plus another 1. So my area comes out to e plus 1 over e minus 2. And just as a check on our work here, I got a decimal approximation of this real quick. That's about 1.09. And the grid on my graph over here is accurate. Each one of those squares has an area of 1. So you have to look at the area that's been shaded here and ask yourself, if you were to chop this up and fit it all into a single square, would it be just slightly bigger than one square? And it looks like it's plausible. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.